Hi there. Thanks again for joining us. This is a Q&A edition of Space Nuts, where we talk astronomy and space science. And in a Q&A edition, you Q and we A, which means we'll answer audience questions. Today, we're going to talk about moving through time. What does that mean? Also, some stuff from Saturn's rings and a sort of hypothetical, not a hypothetical, but not even a what-if question. It's just a question asking our favourite planets and why. Well, that's Jonty's thing. So we will talk about all of that on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And while Fred's away, Jonty is here to play and answer your questions. He is Professor Jonty Horner, Professor of Astrophysics at the University of Southern Queensland. Hello, Jonty.
Hey, how are you going?
I'm very well. Good to see you again.
Oh, it's good. Yeah, no, I've got interesting questions today.
Yeah, we've got some beauties. We might get straight into it. Our first question comes from Rennie in sunny West Hills, California. Hi, Rennie. Rennie's a regular contributor, so we hear from Rennie semi-regularly. Can you please explain what it means to be moving through time? If I theoretically could sit in a chair from birth to death, will I die on a faster timeline than someone who lived a regular, normal life? Is what's aging me about the movement of the Earth around the sun combined with the sun moving around the galaxy, combined with the galaxies moving around each other and my own physical movement? Really, that's kind of a what-if question. We love what-if questions. Thanks, Rennie. Let's open that one up to a little bit of investigation.
Absolutely. And I think the first thing I'd say here is this is such a fun question. It may be well give it a couple of months and ask it again and see whether Fred gives a similar answer to me or not. It's a really interesting one. So the idea of time being a dimension is something that I think makes all of our heads hurt a little bit when we first encounter it, and for most of us continues to do so forevermore. It's one of the fundamentals of the idea of what I guess is often described as space-time physics. It comes out of the work that people like Albert Einstein did with relativity. We're used to the three spatial dimensions: up, down, left, right, and forward and back. Yeah. Although I'm realizing more and more that we actually live in a two plus one kind of existence, really, because we don't look up very often. Part of our common sense is about two-dimensional movement, not three-dimensional, because we think about moving around on the surface of the Earth, and there's all sorts of weird and fundamental things with that. Now, the idea that time is also a dimension is part of that whole thing of space-time physics built into the relativity twins, special and general. And it's a very weird one because with the other dimensions, we choose where to move or we're carried along. We're aware of motion in a way that is changing direction. We can change speed. We feel agency. But with time, when you get told that time's a dimension, you think, but I can't move, I can't choose my motion in it. We're all carried through time at 1 second per second. And so it's like a dimension without agency. It's all a little bit weird. Now, it does lead to that concept of time as a dimension is one of the things that's part of the underpinning of all this stuff, like with special and general relativity, things like time dilation, stuff like this. It's also tied into events and consequences, the logical order of things. A cause has to cause an effect. You don't get the effect before the cause, things like this. Now, this rapidly gets very complicated. And I know at university, when you study physics as a partner to astronomy, or you study relativity as part of an astronomy thing, I know a lot of people find it hugely challenging to get their head around it. And I will openly admit that when I did my relativity courses as an undergrad, my head hurt. It was really, really hard. And particularly in first year, special relativity didn't work for me. And it's something I always say to my students, something I'm very aware of, and something I've said to listeners is that no one explanation will work for everybody. we all learn in different ways, and one source that is brilliant for me might not be brilliant for you. So if my explanation doesn't work, please go out and seek another one. That's no slight on me. It just means that your way of learning and my way of explaining didn't match in that case, and another explanation is needed. And when it came to relativity, I was very much in that boat. I was sat in these lectures, and this is old style education 30 years ago, and it actually is 29 and a half years ago that I was in these lectures, because it was late 1996. Sat there taking notes on paper while somebody's talking at you and writing on a board. So a lot of the information was going through from my eyes to the page without going through my brain, I suspect. Yeah. You know, that autonomous writing thing. Yeah. But it just wasn't gelling for me. The equations are written down so you can use them, but it wasn't making sense. And the course textbook we had was incredibly mathematical because the person who wrote the textbook understood it through the maths, so they explained it through the maths. And that's not the way that I learn. Some people learn brilliantly from maths. I don't. I'm much more of a visual form, a picture form, a metaphor type thinker than an equation is a be-all and end-all. So about the only textbook I ever used in my undergrad days, I was terrible. I'd buy the textbooks, not open them, and then I'd sell them on at the end of the trimester, end of the term, for someone else to take off me and probably do the same thing. But I found a textbook in the library that worked for me and ended up buying it. Now, I was going to recommend it because it was so foundation in helping me to overcome something I couldn't understand. I always think when people are struggling with the relativity stuff, worth recommending it. It's a big book called Space-Time Physics by Edwin F. Taylor and John Archibald Wheeler. And to my shock, I looked it up just before this podcast, and the first edition was published in 1965. So the first edition was launched closer to the publishing of the theory of general relativity and the theory of special relativity than my reading it. Or certainly than we are today, should I say. Absolutely than we are today. It is still in print. And what worked for me was that it didn't go straight to the maths. Instead, it used drawings and figures and thought experiments. And I read it voraciously. It was very readable. I remember it from 30 years ago, and it had an impact. So I'd really recommend that if you're struggling with the relativity stuff. Go to your local library. The textbooks are punishingly expensive, and therefore I'd always recommend people get them from a library first and make absolutely sure. But if you're at all interested in those foundations of how relativity and everything works, I found that book astonishing.
Okay.
That's all getting a bit off the topic, though, but that explains a lot better than I could do the concepts behind relativity that include time as a dimension, include space-time diagrams, which are these weird cone-shaped figures where if you're traveling at the speed of light, you move the same distance in x, which is distance, as you do in time y. So you get a cone opened out like this, and everything inside that cone is moving slower than the speed of light because it's going up the y-axis quicker than it goes on the x-axis. Anything that is nearer to the x-axis of that line is further away from the observer than they could observe it yet, so any light that left that would not have reached you yet. Now, hard to visualize, but if you look into the book, that is what it means. Now, moving in time is talking about our motion on the y-axis of that graph, where we move up it by 1 second every second.
Yep.
That is something over which we do not really have control. I suspect some people would argue that certain substances that can be ingested change your perception of how time flows, so you might be able to control the speed you fly through it there. But that's what we mean by moving in time. It's perceiving time moving forward so that from 1 second to the next, change happens. You know, yesterday is a time in the past. That's already happened. That's a cause. You'll see the effects today. Tomorrow hasn't happened yet. You can't see what is there tomorrow. That's what it means by moving in time. And there's all sorts of wonderful ways people have described it or played with this. Again, you know, I often come back to the Terry Pratchett stuff, and I was just looking at a thread the other day of people talking about their favourite Terry Pratchett quotes. And I'll just try and pull this one up. It's from When the Eternal is Surprised, who was the founder of the History Monks, basically talking about his perception of time. So, man looks at keyboard because I didn't think of doing this. But yeah, this is from Thief of Time, I think it was. Yes. Talking about how when viewed the universe and viewed moving through time as this ancient philosopher who set up the monks of history, who are the people who run around unseen in the background fixing things when they go wrong, because in the Discworld they go wrong all the time.
Yeah.
But said, when considered the nature of time and understood that the universe is instant by instant recreated anew, therefore, he understood, there is in truth no past, only a memory of the past. Blink your eyes and the world you see next did not exist when you closed them. Therefore, he said, the only appropriate state of the mind is surprise. The only appropriate state of the heart is joy. The sky you see now, you have never seen before. The perfect moment is now. Be glad of it.
That's good.
I talk about Pratchett a lot, but I always think that's really beautiful, and it fits in with this concept of time moving irrevocably forward. You can never return to the past and change things. What you can change is the future. When you wake up every morning, it's as though you're newborn into the universe, effectively. Because who is to say that you ever lived before? You know, it may well be that all of your memories were just implanted in you when you woke up this very instant. We don't know. Obviously, the Occam's razor argument is, yes, you existed yesterday and we did do the record the other day. But it's interesting to think of that, and it's a way that people perceive time. Now, moving on to the motion side of it, Rennie, the idea of sitting in a chair from birth to death and how that would affect your life. I'm not a medic, but I suspect if you ask your doctor that question, they will probably tell you that indeed, if you sat in a chair from birth to death, your life would be shorter than if you lived a normal life as a person because of health reasons. I mean, if nothing else, if there's no one around to feed you, it might lead to a relatively short existence. So there is that aspect of it as well. We can't see the future, so we can't predict what our choices are going to do in terms of lengthening or shortening our lives. But there is one way in which your motion can lead to you having a slightly different timeline. So from the point of view of your life or the number of beats of your heart or your perceived time, you'll live the time that you live.
Yeah.
The faster you're moving, though, and this is an outcome of general relativity, motion causes time dilation, particularly motion with acceleration. You know, there's loads and loads of complexity to this. If you are moving faster, the time you perceive is very slightly slower. Now, you then get into rest frames and all that stuff makes my head hurt. So the only place this actually really becomes relevant, particularly in our day-to-day lives and our lived experience, is when you've got a moving platform that's changing direction. So it's undergoing acceleration. Think about satellites circling the Earth. They are circling the Earth. They are moving at a faster speed than we are here on the surface of the Earth. We, however, are slightly nearer the centre of the Earth, so we get a little bit of gravitational time dilation, as I understand it. Our clock runs slightly slower because we're at the bottom of a gravity well, but that is hugely overcome by the fact of the high speed things are moving in orbit. You're talking several kilometres per second. Now, under general and special relativity, you can work out the number of seconds you experience per second that ticks in a certain rest frame using these equations to get the time dilation. And typically that is a vanishingly small effect unless you get very near the speed of light, and then it ramps up. But it is a large enough effect that both we need to understand it and we can measure it. Now, to illustrate the level of this, it's not a huge effect. There's a fabulous stat that there are people who spent time on the International Space Station who therefore technically have experienced less time passing while they were up there than we did on the ground watching them because of time dilation, because of their fast movement and their acceleration and all the rest of it. Space stations go around the Earth, nearly 8 kilometers per second, roughly. A couple of Russian guys were up there for 6 months. They're Sergei Krikalev and Sergei Avdeev. They did 6 months up there, and as a result of time dilation, when they returned to the surface of the Earth, they would have experienced less time passing than the people on the ground did while they were up there.
Yeah.
But not enough for them to perceive. It would have been 20 milliseconds.
Right.
So that's 0.02 seconds and 21,000th of a second. It's not very much, but it has a huge impact on our day-to-day life. And this means that that part of the theories of relativity are among the most tested theories ever to have been developed by humans. And the reason I say that is that every time you use your generic fruit-based device to navigate, anytime you use a sat-nav, you're using GPS satellites. GPS satellites orbiting the Earth allow you to work out your position on a basic level because at any time your device can see signals from a number of those satellites and figure out where they are. There are clocks on board all of them. It can figure out the light travel time to get to it. By seeing the time that they're broadcasting, knowing what your local time is, figuring out the difference between the two, you know how far away the satellite is. From one of them, that places you at any point on a sphere around that satellite that is that distance away. From a second satellite, you've got another sphere and you're where they intersect, which gives you a line. And then a third one brings it down to a point, and the more you have, the more accurate you get. So this is all based on measurement of time, allowing you to measure distance for things that are at a known distance away. This only works, so if you can take into account the way that the clocks are ticking at different speeds, because the satellites are moving in orbit around the Earth. The difference, including relativistic effects and time dilation into the calculations for GPS has, my understanding is it's between a factor of 10 and a factor of 100 on the precision with which your location can be calculated. And your GPS is usually good to probably about a meter. I think some of the modern ones are even more accurate than that. So if you imagine that, let's take the really optimistic case that you're only getting a factor of 10 improvement by including relativity. At the minute, you've got an accuracy of 1 meter, and that's good enough for you to navigate. With 10 meters, it probably wouldn't be. With 100 meters, it certainly wouldn't be. So our GPS systems only work because of our level of understanding of relativistic motion and of time dilation. So those satellites moving very, very quickly around the Earth are experiencing an infinitesimally small amount of time dilation compared to the things they're broadcasting to on the surface. And we have to factor that into our calculations to navigate. So your sat-nav wouldn't work without the theorems that Albert Einstein put together more than a century ago that are all about how things move through time.
Yeah.
So hopefully that has answered that question. I think, Rennie, I would be very tempted to suggest that at some point you try and get Fred to answer that as well, just to see where he took it. But hopefully that at least is helpful. And like I say, if the relativistic stuff really interests you, space-time physics, even though it's a book that was first published 60 years ago, I found invaluable in getting me through the exams and actually allowing me to get out of my first year and pass rather than being kicked out of uni. So it was a great book.
Rennie might also like to go on Wikipedia or any number of platforms and look up the twin paradox. That's a fun one. That's a great thought experiment. And I think there were twin astronauts that have had a little bit of a separation in age because one of them spent much more time in space than his brother. So their age difference increased by 8.6 milliseconds or something like that.
I've seen
really
actually,
interesting.
There are a couple of, there are many science fiction books that play around this. I've spoken before about this series of science fiction books called The Masterworks of Science Fiction, which was an attempt by a publisher to make money, obviously, but also to bring back some classic science fiction that is regarded as being very good. And, some of the things I read are very fun, but they're not necessarily very good. There's always that side of things. And I'd say the Chrysalis books I'm reading at the minute, the guy incarnated into the body of an ant, that's very good fun. I'm really loving it, but I wouldn't necessarily say they're high literature. They're fun. The Pratchett stuff is a bit of both. But these masterworks of science fiction are often fascinating because they are quite often hard sci-fi. So in other words, they're science fiction that is grounded in our understanding of science at the time they were written and tries to use the laws of physics to help build the narrative rather than waving the laws of physics to allow the narrative. There's a fundamental difference between the soft and woolly sci-fi and the hard scientific sci-fi. And two books in particular that leap to mind when we're talking about time dilation and relativity and things like that are The Forever War by Joe Haberman, I think his name was. I'll just put that name up. The Forever War was basically, Joe Halderman. The idea that there is, it's written in 1974, it's called military science fiction. And the idea is humans are fighting an interstellar war against these alien civilization. And they're sent off on missions on spacecraft that travel at relativistic speed because it takes a hell of a long time to get anywhere. And it's not really about what they do when they get there. It's about what they do when they come back. Because the time you've gone there and come back, the Earth has moved on hugely. You've been away for 5 years, but Earth has skipped forward 100 years. can you reintegrate? How has society changed? And I think it's fair to say that without a spoiler, the motivation is that you've more in common with the people you've lived that experience with than you do with everybody else. And it's all about that, grounded in this knowledge of time dilation. I've travelled there and back again and come back to a world that is changed. The other one that really stuck in my mind as a interesting way to get your head around time dilation is a book called Tau Zero by Poul Anderson. And I think that was published even longer ago. I think it was probably in the 1950s. And part of the reason I can say that is that that book, I believe, predates the Big Bang Theory, or it's around the time of the Big Bang Theory. It's based on a short story published in 1967. The book itself was published in 1970. So it's a fabulous exploration of, it was actually post-Big Bang, but it's a fabulous exploration of relativity in an unusual circumstance. In this case, it was people being the first humans to travel to the stars on a spaceship that was meant to go to a star and then come back and report. They were aiming to reach Beta Virginis. It says crew of 50, 25 men, 25 women, using something called a Bussard ramjet. So you have basically a rocket that scoops up fuel and burns it to go faster and faster, right? But there's a problem. They get up to high speed and then something breaks, but they're going so quick that they can't get outside the spacecraft to fix it. And so they just have to go quicker and quicker. And so it explores this captive group of 50 people on an island in the universe that cannot stop, can only go quicker and quicker as the universe moves around them. And of course, by continuing accelerating, they get closer and closer to the speed of light. And time dilation impacts them more and more. So they see the universe to the end of the universe and beyond within a human lifetime. And, you know, the cosmology in it has changed. It was at a time where the Big Bang, a lot of people thought, would end up in a big crunch, that everything would stop expanding, fall back together. But it's, again, this awesome way of demonstrating how relativistic terms work. And the crew on the mission before anything went wrong were aware that when they returned to Earth, something like 33 years would have passed before they get to their destination, this star, but for them only 5 years would have passed. So when they turn around and come home, they'll have aged 10 years, but 66 years would have passed on Earth, give or take.
Yeah, that's...
In fact, that doesn't happen. Wonderful book.
Yeah. I love those sorts of stories. I love time travel, sci-fi, and all those relativistic concepts. I'm actually just finished writing a trilogy, and I'm just getting it proofread at the moment.
Fabulous!
And there's a little bit of that in it, but I'm not giving anything away.
So maybe without any spoilers at all, that in a few years' time, maybe I'll be picking up your books as part of the Masterworks of Science Fiction.
You might. That'd be nice, wouldn't it?
No pressure.
No, well, okay. Thanks, Rennie. Enjoyed that question. It's a fun one to talk about. This is Space Nuts with Andrew Dunkley and Professor Jonty Horner. Let's take a short break from the show to tell you about our sponsor, NordVPN. Let's talk about your online security. Now, I can tell you from personal experience, last year when Judy and I were overseas, we ran into a bit of a frustrating issue. There were certain apps we simply couldn't use without a VPN connection, things like our banking apps. They wouldn't load, and even a sports app I rely on wouldn't let me watch games back home because of geofencing and things like that. So with NordVPN, I was able to watch football back home while crossing the Atlantic Ocean. It was pretty weird, but it worked. And NordVPN is the best in the business. With NordVPN, you can securely connect to servers all around the world, which means your apps think you're right back home, even when you're not. It also encrypts your internet traffic, hides your IP address, and keeps your personal data safe from hackers and trackers and anybody else who's trying to get at you online. And this can happen in public Wi-Fi situations, in hotels, airports, cafes, anywhere like that. The best part, it's fast. Thousands of servers globally, and their NordLynx technology allows you to run seamlessly. No slowing down. It is brilliant. Right now, you can grab the special Space Nuts deal through this URL, nordvpn.com/spacenuts. You'll get 4 extra months free plus a 30-day money-back guarantee. So there's absolutely no risk if you want to give it a go. That's nordvpn.com/spacenuts. Stay safe online with our sponsor, NordVPN.
I think we need to do a little more all-weather testing. Amen.
Space Nuts.
Our next question, Jonty, comes from Paul in Brisbane, although he doesn't call it Brisbane. You've probably heard this term because you live so close to Brisbane, but overseas people might think, what on earth is he talking about? He said, G'day, Space Nuts. Paul from sunny Vegas here. And he's thrown a challenge at me. Before I ask my question, could you read it in a Queensland accent to make it sound authentic, Andrew? I'll give it a go, Paul, but, it's been a long time since I lived in Queensland. I was thinking, just listening in episode 601, when you and Fred started talking about the possibility of Titan and Hyperion colliding, thus creating Saturn's rings 100 million years ago. What do you reckon the odds are of some of the bigger blocks of the collision spinning off into space, getting closer to the sun? I don't know, colliding with the Earth, say, 65 million years ago. Is that a possibility, or does the chemical residue from here on Earth suggest there's more likely to have been a comet? Curious to get your thoughts on this, eh? As always, keep up the great work and thank you. Was that Queenslandish enough?
So the accent thing, and again, we're very good at getting off topic, or I am.
Depends what part of Queensland, though, because it's a big state.
For people listening,
and you've got to chuck in an A on the end of every sentence.
One of the things that's always made my head hurt a little bit since I moved to Australia in 2010, and I'm officially Australian,
Yeah.
It's a lack of diversity in the accents. I grew up in the UK where accents are very, very varied to the extent that you could tell within my school which estate people grew up in because of subtleties in their accent locally. And the variation on a larger scale is astonishing. It's part of why I think British actors have so much success, partly because they get very good training, of course, but if you're an actor in the UK, you have to have a fluidity with accents because there's such a diversity just within the UK.
Yeah.
I came to Australia and I've lost some of my ear for the UK accents. I used to be really good because you grow up there, it's a natural thing. I've lost a bit of that. But over here, it seems to be, there isn't a very strong regional diversity. There's just a little bit of town versus country and a very little bit of north-south.
Yes.
But it's very smooth,
although
very little variety.
I'll tell you, when I got into radio, I did a demo tape, and I had a friend listen to it who'd been in radio a very long time, and I was only just starting out, and he listened to it and he said, you've got to get rid of your Newcastle twang, because I grew up in the Hunter Valley in that Newcastle district. And I said, what? He said, you've got a Newcastle twang. There's a certain sound that comes out of the mouths of Novocastrians. I had to train that out of myself, and it can be, no disrespect, but it can be a bit grating. But there are diversities in accent across Australia. That when I worked for the ABC, they actually published a map of accents.
Yeah.
And I think the most prominent variation is South Australia, particularly Adelaide. Much more posh.
But it's also, to me, it's much more evidence because I just don't quite have the ear for it. Because in the UK, the accents are very much more varied. So Newcastle accent to me is very different to what you'd think of a Newcastle accent. But where I see it is in language. So there's the perennial argument among Australians of whether it's a potato cake or a potato scholar. Is a good example. So you've got regional things like that. Yes. And from my side of things, I worked in Switzerland for 3 years and shared an office with Hagar, who was this young woman from, I think, Iran or somewhere Persian. I'm not sure exactly where. But we communicated in English, which was her 6th language.
Wow.
Which was astonishing to me. But there was one time I'd been on the phone to my parents and I finished and she said, so Jonty, what does A up mean?
A up.
And yeah, A up. It reminds me of the wonderful...
Isn't that Liverpudlian?
Well, A-up's Yorkshire as well.
Not far apart.
If you want to see the accent of roughly where I grew up, incidentally, it's worth people looking up the fabulous song Ilklim Bartat, which is a cultural treasure from my part of the world, and we all learned when we were in Scouts and at school. And it's basically a group of fellas at the pub saying, where have you been since I saw you last? You've been caught in Mary Jane, and it goes on about how he's not been dressed appropriately and he's going to die and they'll have to bury him. But it's all in very strong dialect, so you can see that. But what that resulted in is everybody in Bern communicated in English at the Physikalisches Institute. I had to speak German when I was out in the town, but English has become this kind of lingua franca there, because Switzerland's a country with 4 different languages. It's got French, German, Italian, and Romansh. But everybody's proud of their language. The French speakers will not sully themselves by speaking German to the German speakers. The German speakers, therefore, will not sully themselves by speaking the foul French to the French speakers. Yeah. So they speak English. But that means people have very good English, but they've learnt a lot of their English from watching American TV rather than British TV. But even the British TV is a little bit denuded in terms of accent and in terms particularly of dialect terms. And it was to an extent we were talking about the accents. The news presenters until about 20 or 30 years ago on the BBC had to use received pronunciation, which is the Queen's English, and you have to speak very properly. And they got rid of that because people realised that actually diversity in accents represents the diversity of people, and that's great. What that meant, though, was my accent, I've reliably been told, is relatively strong, but I don't really use any dialect terms anymore, other than the odd bit of Aussie stuff I've picked up. Because what was really throwing people in Switzerland was the dialect terms, not the accents, things like A up. And so my language has shifted. I've lost a bit of an ear for the UK stuff, but I don't hear much variety in the Australian accent. Now, part of that is because I'm not from here, but I always find that kind of stuff really, really interesting. So, I mean, I could tell you were getting a stronger Australian accent, but it wasn't necessarily, I couldn't have told you where it was from. Other thing is, again, saw an interesting discussion online about the Australian accent changing over time, asking why when you watch Aussie films and TVs from 30, 40, 50 years ago, everybody almost sounds like they're a pastiche of the Australian accent. It's so full on, and there's so many terms and insults and stuff that aren't used today. Yeah. Apparently part of it is language evolves. We've got all these multicultural influence. We've got all that stuff. But also apparently the actors were trained to ham it up.
Oh, absolutely. That's exactly what it was. And see what you started, Paul. But I understand, because I did some research on it, the Australian accent came about because we were a colony of convicts brought over from the UK. But the convicts were all from different walks of life, but they were conglomerated into a new community. And all their accents merged into what is now the Australian accent. So, you know, you had Welsh, you had Irish, you had Scottish, you had English, with all their variations, all coming together and creating the Australian accent. So that's why it is what it is.
Yes.
But it's ever evolving too.
It is a wonderful thing. It does change over time,
yes.
Which I found interesting. Anyway, sorry about that. We get off topic wonderfully well. Saturn.
We're good at that. So Fred started talking about the possibility of Titan and Hyperion colliding and what happened to the stuff. Could a big rock from that event have hit Earth 65 million years ago? And you know what he's talking about there. Or did it all just go flying off into space? Or did it do something else, et cetera, et cetera?
All sorts of ways we can go with this. So the origin of Saturn's rings, first and foremost, is not yet definitively known. We know that there are ring systems around Jupiter, Uranus, and Neptune as well. We suspect strongly that in the past and in the future, Mars has had and will have rings. I think Red Dwarf will have, possibly going to have, whatever. It may have had episodic rings in the past. We found rings around a few of the solar system smaller objects like the Centaurs, Chiron, and Chariklo. Rings are a thing. We've also found potentially rings around exoplanets. Some debate about that. We find rings around stars in the form of debris disks and all the rest of it.
Yep.
Ever since Saturn's rings were known, there's been ongoing, how did they get there? And there is an ongoing, not only how did they get there, but are they transient or permanent? And there are a wide variety of opinions on this, and modelling has not yet come down strongly one way or the other. Currently, the best thinking about Saturn's rings is that they are more likely to be new than old. So we're probably seeing a ring system that has in bulk not existed since the birth of the solar system. And estimates of the age range from 10 to 100 to 300 million years. These estimates on the rate at which the rings are being depleted suggest that they may well return to the level of Neptune, Uranus, Jupiter-type rings within about 300 million years from now. Those theories, those arguments, would suggest that if the ring system is younger than the age of the solar system, there had to be an event to bring it into being, obviously. And there have been a number of different suggestions to cause this. One is that, and this was commonly argued when I was a kid learning about it, that Saturn had a comet or asteroid that got too close, was torn asunder, creating the rings. Now, this invokes a part of planetary science knowledge and physics called the Roche limit, which is essentially if you have two massive objects and you bring them close enough together, tidal effects will disrupt the smaller of them due to the gravity of the bigger of them. And the point there is if you think that the strength of the gravitational pull falls off as the square of the distance, and you've got an object that's 100 kilometers across, the side that is nearer a planet will be feeling a stronger pull than the side that's further away. Now, depending on the strength of the object, that distance will vary. The stronger the object is, the closer it can get to a planet before disruption. But we have this concept of the Roche limit, and Saturn's rings are within the Roche limit, which is why they've been disrupted. And the largest objects in them are probably, to be honest, the Shepherd moons that are kilometre-scale objects, which are probably, due to the nature of the Roche limit and stuff, they're probably fairly robust rather than rubble piles, because if they're rubble piles, they get disintegrated. So they're probably at a distance where they are within the Roche limit for a fluid object that has no strength, but they are strong enough that the Roche limit for them will be closer in. Anyway, a bit off topic there, but that's the physics behind it. And you can work out that Roche limit either as a ratio of the mass of the object to the mass of the thing, it's the bigger thing that it's coming near, or as a ratio of the densities. It works either way, which is kind of cool. That's what the physics is behind why you don't have a single object there. It can't form a single object. It's got to be broken up into debris. The rings are decaying. Dust is lost to Saturn all the time. They're also being slightly replenished by the activity, particularly of Enceladus, which is repopulating the E-ring. So they're a system in flux, and it's not clear exactly where they formed. There was the idea when I was a kid that it was a comet or asteroid that was disrupted to make that much material. I think that has gone probably by the wayside because you need a way to dissipate the energy for an object to be captured. So if you have a comet or an asteroid get close enough to Saturn to be torn apart, that material is still moving faster than Saturn's escape velocity, so it will just fly away, albeit torn apart.
Right.
If you have something that is temporarily captured as a satellite, it'll be on a fairly elongated orbit if it's going to get close enough to be disrupted, and it will continue to follow that. So if you look at Comet Schumacher-Levy 9, back in the 1990s, it came very close to Jupiter in 1992, I think, was torn apart so that we had many smaller comets that all followed essentially the same orbit in a lengthy chain and fell apart, crashed into Jupiter one after the other over the space of a couple of weeks in 1994.
That's right.
They didn't form a ring system.
No.
When that had its first approach to Jupiter, it was torn apart, but it didn't make a new ring system. So you need some way to dissipate the energy to trap all the debris onto a circular orbit near the planet. And it's very hard to visualize how you do that from an asteroid or comet passing through. So that's led to, instead, the idea of the collision between two moons. Now, the most recent version I've seen discussed of this is that there was a moon that was possibly as large as Hyperion or even bigger, that collided, whose orbit spiraled inwards to the point it crossed the Roche limit. Now, we're seeing this happen with Phoebe, the innermost of Mars's two moons. Phoebe is closer to Mars than what we call the co-rotation altitude, which means its orbit around Mars takes less time than Mars takes to spin. And when you're closer than that co-rotation place, tidal forces will make you spiral inwards rather than spiraling outwards. Our moon's further out. It takes longer to orbit the Earth than the Earth takes to spin, so it moves away.
Yeah.
Imagine then that you had a moon a few hundred kilometers across, 200, 300, 400 kilometers across, close in, that spiraled inwards and crossed the Roche limit. It would be disrupted from a ring system. That's one theory. Another is that you had a moon that was pretty close in, that was then struck by an object large enough to shatter and disrupt it. But collisions of that size would be relatively rare these days because projectiles big enough to shatter a moon of that size are relatively scarce. A more recent version that's been proposed is that you had a much larger object, something more like the size of Titan, and that was stripped off during the formation period of Saturn. There's all sorts of theories here. But like I say, we're not fully there yet. We're still exploring. That's where future missions to Saturn are going to teach us a lot more. We've got an age here. Observations based on the Keck telescope suggest that the rings will be gone in 292 plus 818 minus 124 million years, which illustrates that as astronomers, we are terrible at choosing significant figures, and I tell my students this all the time, because if you talk to a physicist, they'd see those numbers and weep, because they'd say, well, that should just be 300 plus 800 minus 100, because the other numbers are meaningless. Anyway, but it's a very large uncertainty on how long they will take till they're gone. We don't know how massive they were initially, and how massive they are initially will be part of what determines how long they've been around. Anyway, so that's why there's still a lot of misunderstanding and a lot of confusion there. And it may well be that rings of the scale of the rings of Saturn around the giant planets are an episodic thing. It may well be that planets like Saturn, Jupiter, Uranus, and Neptune have minor ring systems all the time, but occasionally we'll get a really good one. And it could be that in the past, Jupiter had a massive ring system like this, and in the future, Uranus might, for example. Mars will probably get a ring system when Phobos gets close enough and is disrupted. All that now to aside, the next part was about debris reaching us from the collision and reaching the Earth.
Yeah.
Two parts to this. The first is that some material from that collision could potentially have reached Earth. I don't doubt that. I did work while I was at the University of Bern, which we talked about earlier, with a PhD student at the time called Augustin Anich, who was doing simulations of the giant collision that made Mercury the planet we know it is today. Mercury is overdense, it has an oversized core, and the thinking is it was probably once a planet twice the diameter of the current Mercury, and it had this massive collision that stripped it of its mantle and crust, leaving behind a core with a little bit of rubble on top. And he was doing simulations of that impact. And my contribution was I ran orbital mechanics simulations. This is kind of core to my day-to-day work. This is what I've done all through my career. And I said, where would the ejector go? If you have a collision like that, some of the material ejected will be traveling at less than the escape velocity for all of the mass that's around, so that material won't be lost, and it would either, in the case of the Earth-Moon collision, form a satellite like the Moon, or fall back and contribute to the reaccretion. Material traveling above the escape velocity will escape and go into orbit around the Sun. And at that point, it is subject to all of the dynamics that goes on, the gravitational interactions with all the other planets. And I ran simulations of the ejector to see what their eventual fates would be, where they would wind up. The majority of the ejector from the Mercury-forming collision hit the Sun or was flung from the solar system, never to return, as a final fate. That's where it ended up. But about 2% of the material ejected from Mercury would have landed on Earth. Ooh. So we will have been polluted by the Mercury-forming impact by what you describe as Hermian material. If we were talking about Venus being venereal material, which then became Venusian material, Mars being Martian, Jupiter being Jovian. For Mercury, Mercurian never quite worked, so a lot of people used to call it Hermian. It's their traditional name for it. But anyway, the material from Mercury, about 2% of it would have rained down on the Earth. Now, this ties into the work that I've talked about before about panspermia as well. Material ejected from one planet becomes objects moving freely within the solar system, subject to the gravitational pinball that goes on. If you have a collision in orbit around Saturn, if it is a collision between two of Saturn's moons, the overwhelmingly vast majority of ejecta will stay bound in the Saturn system, because the moons are both themselves very deep in Saturn's gravity while very tightly held. So the vast majority of ejecta from two moons colliding with each other will be kept in-house. But that's not all of it. Also, some of that ejector in the Saturn system will be like ejector in the solar system. It'll be bounced around and moved around by the gravity of the moons. So a tiny fraction of it could eventually be ejected that way as well. If you have a collision that instead involves or invokes an object that is not currently orbiting Saturn, but is a comet or an asteroid passing through, that object itself is moving faster than the escape velocity of Saturn, so a significant amount of the ejector also will be. In that case, you'll get more material put into orbit around the Sun. Once the material has escaped from Saturn, it is moving on an orbit that makes it one of the centaurs, and the centaurs are one of my favourite populations of objects anywhere because they're what I studied for my PhD, and I did the same dynamic simulations of them. Where do they come from? Where are they going? How will they get there? The centaurs are the parent population of the short period comets. The centaurs themselves are daughters, sons, children of the trans-Neptunian objects. Moving around in the outer solar system means scattered inwards. In my simulations of the centaurs, about 1/3 of centaurs, which is about 1/3 of those objects between the orbits of Jupiter and Neptune that are on unstable orbits, about 1/3 of them will eventually become a Jupiter family comet, will be flung into the inner solar system, usually by Jupiter, which means it'll be put onto an Earth-crossing orbit, which means that if you eject enough material from the Saturn system, some of it will hit the Earth. It'll be a vanishingly small amount. It is unlikely, though, that you'll get a chunk big enough to cause a mass extinction, making it all that far. The thing that killed the dinosaurs was about 10 kilometers across. We think maybe even a little bit bigger. That's a very, very, very big bit of stuff. Now, obviously, there's a small chance it could have been the result of something like that. There are suggestions that the thing that killed off the dinosaurs might have been an asteroid that was probably produced in a collision in the asteroid belt and being a member of one of the collisional families that feed material to the inner solar system. Others have suggested it could be a comet. It could potentially have been a fragment of a smashed moon, like Paul is suggesting. It could have been a very ancient fragment of the Mercury collision that had managed to survive 4 billion years, but that's vanishingly unlikely. Of course, things are ejected on a much shorter timescale, so there'd be nothing left, effectively. But we don't know. That's a fundamental thing. What drives the understanding that the impact itself was extraterrestrial was initially the iridium layer that was found globally. That was kind of a bit of a smoking gun. At the point of the mass extinction in the fossil record, they found the crater. You cannot tell from the crater's size alone what the nature of the impactor was or the impact speed. Now, for a crater that old, it's a bit impossible to do anyway. I've been really interested, and we've never got around to doing this as research, to talk with people like the crater counting people to see if there is any way for bodies like the Moon or Mars, where there's much less weathering, to distinguish between a cometary or asteroidal impact on the basis of whether the speed's influence on the kinetic energy of the impact can modify the crater formation process. Probably it can't, because effectively you're dumping X energy into the surface, and that's what makes a crater. But I've been interested in that. But what that means from the Earth's point of view is that from the morphology of the crater, from what's left from that impact, we cannot tell what the impact was or how fast it's travelling. Had to be faster than the escape velocity of the Earth because it came from beyond the Earth. So the minimum speed is 12 kilometers a second. It is almost guaranteed that it was a solar system object, not an interstellar comet like Comet Atlas, which means that the maximum speed it could have hit us is 72 kilometers a second, which is, you get that number by combining the orbital speed of the Earth, which is 30 kilometers a second going forward, with the maximum speed that something could be traveling at 1 astronomical unit at our location and still be bound to the Sun, which, if you work out the velocity, if you're going at 42 kilometers a second at the location of the Earth's orbit, you're right on the boundary between the solar system's escape velocity and not. So anything faster than that will escape. Take those two numbers and say, right, you've got an object coming head on at the fastest speed it could have and stay bound to the solar system. 42 kilometers a second one way, 30 kilometers a second the other way gives you 72 kilometers a second. So we know the velocity with which this thing was coming in within a factor of 6. Most likely it's at the lower end because we get more asteroidal impactors than cometary ones. But we don't really have much more than that on the composition of it. There is a lot of debate over whether it was cometary, whether it was asteroidal. An object formed from part of one of the moons of Saturn would be ice-rich, and so it would look like a cometary impactor. So I'm not sure, for an impact 65 million years old, whether we would ever be able to distinguish between a fragment of one of the moons of Saturn as the impactor and a comet as the impactor. I just have no idea how we would do that. What we would probably be able to do is if we went to a near-Earth object, whether it's a comet or an asteroid, and took samples, there is a potential that then maybe through isotopic analysis we could tell that something was a fragment of a Saturnian moon, but we need things to compare that to. That is very much on the very fringes of what we can do. But we do that a little bit with some meteorites. There's a couple of families of meteorites where we think we know the parent object. And these meteorites are compositionally grouped together with such tightness that they are distinguishable against the compositions of everything as a background. It's like if you measure the composition of everything and they're points on a wall, these ones all grouped together, so they come from the same parent. But I don't know how we could figure out whether it was a fragment of a Saturnian moon versus a comet. If we got to the point where we could distinguish comet versus asteroid, I think the argument would be it's a cometary body probably, but we couldn't tell you whether it's a short or a long period comet, but people will probably come down on the cometary explanation rather than the fragment of a moon explanation because of the Occam's razor thing. So if you've got two explanations that are equally good at explaining the story, you take the one that's simpler.
Yeah.
That might not be Occam's razor, but that's one of those philosophical constructs that, you know, it's a more complex and challenging route to get a fragment of a Saturnian satellite to kill the dinosaurs than it is to have it just be a normal comet.
Yeah, fair enough. All right. Very good. Thank you, Paul. I think we covered that topic very, very well. And I hope all's well in Queensland. Hey, we're going to take a breath and then we'll quickly go into our final question here on Space Nuts.
0G, and I feel fine.
Space Nuts.
And we're with Professor Jonty Horner today with Fred Away, a Q&A edition. One last question. We'll have to make it quick because I think we've really burnt the clock today. Too much talking about accents, I think. I have a question.
I was just going to say, talking of accents, get Fred to sing Il Climo Batata. Because he's from my neck of the woods originally.
Okay. I have a question that might come across as lame or childish. Yes, it did. No, it didn't. But I'm hoping that a professor and a genuine space nut, or I'm hoping that asking a professor and a genuine space nut this question, it might prompt for a much more interesting answer than the average Joe. What is your favourite planet in our solar system and why? I wish I could give you an interesting answer myself. I do find Jupiter fascinating and Europa. Okay, I know it's a moon, but I'm intrigued by what could be under all that ice. Hopefully, we'll find out in my lifetime. So yeah, childish question from a 40-year-old, but hopefully you can turn it into a more deep and meaningful answer. That's Dan from the Gold Coast, also a Queenslander. I can go first and be very quick. I'm fascinated by Mars. I just find the geography outstanding. A smaller planet than Earth with geographic highlights that are just mind-bogglingly huge, like the Olympus Mons, for example. That is a volcano that it's the biggest in the solar system. And I think it is so high that it's actually sticking out of Mars's atmosphere. The canyons on Mars, and there's more than one, but there's the biggest one dwarfs the Grand Canyon on Earth. Like I think you can fit the Grand Canyon in one of its tributaries, and the list goes on. It is a fascinating planet. I always like to think of it as that was God's first attempt and he stuffed it up and then we came next. And because we've been able to send so many probes and rovers and satellites to Mars, we've been able to document it, get some incredible high res pictures of it. I just find it a beautiful, beautiful world. And I mentioned my sci-fi trilogy earlier. Mars is in it. I couldn't leave it out. So Mars for me. That was a quick answer. What's yours? It's got to be in the solar system.
It's a really tough one, and these kind of questions throw me because it might be a childish question because it's the kind of questions kids ask, but it's entirely a good question to ask. I'm not as broken by this. While I was over in Switzerland, met up with an ex of mine whose daughter's now 9 or 10 years old, and her daughter's doing English in school, and all well and good. And she wanted to practice her English and was talking to us a bit in English. And kids ask you, what's your favourite colour, things like that. She asked me what my favourite fruit was. And I was just broken because I've never really thought of that. And it took me like 2 or 3 minutes to kind of, it just put me into this head jam. And I didn't know an answer. This one's a little bit like this. And to me, this question's a bit like asking somebody with a large family who their favourite child is, or asking someone who their favourite pet is. Now, I suspect I don't have kids, but I think the favourite kid varies from time to time with people who've got parents, and they'd never say they have a favourite, but there's a little ranking scale. It's Nanny Ogg and her extended family in the Discworld series, where you could tell how in favour people were where the trinkets that they bought her were in the house. And, you know, heaven forfend that the little thing you brought back from holiday ended up on the coffee table outside in the hallway, because that meant you were really in the bad books. I really struggle to answer questions like this because they're all fascinating in different ways. You know, there are things that we can really get from them. Mars, from an astrobiology point of view, is really the obvious answer because it's the place that we'll look for life elsewhere. Jupiter's the obvious answer because it's been fundamental to a lot of the research I've done in terms of the question of Jupiter, friend or foe. It throws a lot of comets our way. It's the source of, therefore, indirectly, the cause of many of the meteor showers and many of the meteor storms and stuff we see. They would be contenders, as would the others to a certain degree. Neptune, because it's a fabulous insight into how science can change over time and how we can discover things without seeing them. Neptune kind of presaged the exoplanet era because we discovered Neptune not by seeing Neptune, but by observing Uranus misbehaving and inferring that Neptune had to be there to cause that misbehavior. Although there are some suggestions that Galileo actually saw Neptune in 1610 and should be credited as the discoverer, but didn't realise what he had. There's a background star marked on one of his drawings, I think, of the Galilean moons, the moons of Jupiter, where there is no star, and people think it was actually Neptune.
Wow.
So there are some suggestions Galileo was the discoverer of Neptune.
Interesting.
But for me, Neptune's fascinating because of that indirect discovery. But I think for me, if you really push it, I probably have to say the Earth.
Oh.
And it's the Earth because we is here. Yeah. But the Earth is the place that's driven all that complexity in terms of life. And if you think about Mars being a complex place, the Earth is even more so because of the influence of the water and the atmosphere, the weathering and the plate tectonics. You know, so it's my favourite from the point of view of it's the only place I can sit around comfortably in shorts and T-shirt and chat like this. Also because it is the window into the future of our knowledge of life elsewhere, and it's the cradle of everything we know and everything we've experienced. I do have a deep and abiding love of the Earth from that point of view, but also as a scientist, the Earth is fascinatingly complex compared to the other planets. It's the only planet on which we observe plate tectonics.
Yeah.
Therefore, it's the only planet whose surface on long time scales is that degree of changeable and mutable. You know, if I brought you back, say we did play with Rennie's question from the start a bit more. We built the spacecraft from Tau Zero, we accelerated, had a problem, couldn't slow down, eventually managed to fix it, came back, and we came back in 1 billion years' time. Mars would still look like it does today. Unless humanity terraforms Mars, Mars would look like it does today. Venus would look like it does today. All of the planets would look like they do today. Saturn's rings may have gone, peripheral things like that will have gone, but the Earth would be unrecognisable. With continental drift, the Earth wouldn't look like home. And even with the change in the atmosphere, the Earth may have changed. I've seen some suggestions that when the Earth was young, the oceans weren't blue, they were green.
Yeah, I've heard that.
That's how much the Earth has changed. The mountain ranges will have shifted. I always find it fascinating to wonder what is the biggest mountain that the Earth has ever had. And you Google that, that's been asked a lot. Nobody's really got a strong answer because a lot of it depends on the elasticity of the Earth's interior and the energy available for plate tectonics. Because the limiting factor on the height of a mountain on Earth is the sinking that you get as a result of the mass of the mountain and the weathering that we get that wears it away. On Mars, you don't have that with Olympus Mons. There's no weathering. So it could just get bigger and bigger, even though it will have a very deep root. It could keep getting bigger because there was nothing wearing it down again. So I think for me, because of the complexity and because it gives me a place to do my astrophotography and live my life and all the rest of it, the Earth would have to be the top of the list. But trying to pick a planet other than the Earth is a bit like trying to pick your favourite pet or your favourite child. And it might be that you have one internally, but heaven forfend you tell them.
Very good answer. Very good answer. And I love the question. So not childish at all, and appreciate you sending it in. And if you'd like to send questions in to us at Space Nuts, jump on our website, spacenuts.io or spacenutspodcast.com and click on the Ask Me Anything button at the top. It's just labelled AMA. And while you're there, have a look around, check out the shop, sign up for the newsletter. See if you want to become a supporter, that's optional. And please leave reviews wherever you listen to us. And that'll wrap us up for another episode. Jonty, thank you so much.
That's a pleasure. Thank you for having me.
Always a pleasure. Professor Jonty Horner, Professor of Astrophysics at the University of Southern Queensland, And here in the studio, couldn't be with us today. He realised that Earth wasn't his favourite planet, so he left. And from me, Andrew Dunkley, thanks for your company. Catch you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.